We often wonder whether we can live in space. Many scientists have proven that it is possible, but we need to adapt our new home with our biological structure. We have evolved for millions of years in an environment that attracts us downwards. The lack of gravity in space, or microgravity, is a total twist. So is it possible to create artificial gravity? Space is fascinating. It's seemingly infinite and hosts the most complex properties we'll ever seen. But space is also a hostile place. Gravity doesn't exist or is nearly inexistent there. If we want to go into space, we have to create from scratch a new type of gravity. An unnatural gravity that will have the exact same effects than the actual one. Creating gravity isn't an option, it's a must. Gravity is primordial for the welfare of the human being. First, what is gravity? How does it work? Gravity is a natural phenomenon that attracts any bodies with a mass or energy towards each other. For example, the centers of two planets. On Earth, we stand on the ground thanks to the net acceleration. This is the combined effect of gravity and the centrifugal force caused by the rotation of Earth. In our planet, the value of our acceleration is about 9.8 meters per squared second. That means that if we let an apple freely fall from a building and took away the air resistance, the speed of the fall would increase by 9.8 meters per second every second. This concept was mostly worked by Newton, a British physician, mathematician, philosopher, alchemist, astronomer and theologian. One of the first things that astronauts complain about is nausea or vomiting. This effect of the lack of gravity on the sensitive inner ear affects balance, coordination and spatial orientation. It also affects your ability to track moving objects. Being in space is like standing on your head. Fluids tend to pool in the upper part of your body, giving you a swollen face. It is similar to when your ankles swell on a long-duration flight because fluid pools in your feet. Your body preferentially drives fluid towards the upper part of the body. When you're in microgravity, all those systems still work to push fluids to the upper body, unopposed by gravity, so you get this swelling of tissues in the head. As the gravity slips away, it starts to deteriorate. In addition to physical problems, there are psychological problems. Time perception is impaired, and a lack of gravity causes alienation, desperation, excitement and behavioral disorders. We have talked earlier about the centrifugal force, but what is it, exactly? The centrifugal force is the force that makes objects move outwards when they are spinning around something or traveling in a curve. This is the effect that happens when you, for example, sit in a car that's turning. Your body, due to the first of all three Newton's laws, keeps its movement in the same direction and with the same velocity. This is called inertia. If we threw an apple into space, it will never slow down, never accelerate and never change direction. It will keep the exact same movement forever as long as it is not attracted by an external force, which is nearly impossible in real life. This force could be used as a clue for our artificial gravity, as the movement going outwards could actually be our artificial net acceleration. Let's adapt that concept in a spaceship. We need a shape, something that is circumferential and spinnable. This shape is called a torus, and it is our new spaceship. It looks like a road as a circle. The occupant will feel the exact same effect as in a car constantly turning to the same direction. Yet, we don't know the adequate size, thus the radius. We don't even know the acceleration, nor the speed. Thankfully, nowadays we have all the mathematical tools needed to determine these theoretical values. First, we need to determine a radius. But we have to take into account the gravitational gradient. The closer you are from the center, the more attracted you get. If the radius is too small, the difference between your feet and your head will be huge. The taller the radius, the better. To reduce that effect, we need a radius of at least 200 meters. To satisfy our craziness, let's set it to 1000 meters. If the radius of the torus is r and the tangential velocity is v, according to physics properties, the acceleration towards the center is v equals 99.04 or 99 meters per second. So, our torus must have a tangential velocity of about 360 km per hour or 223 miles per hour. How many revolutions per minute is it? The tangential velocity v is the angular velocity w times the radius r. So that gives us a velocity of about 0.01 radians per second, or 0.57 degrees per second. You then need 10 minutes to complete a total rotation of the torus. In a nutshell, that's all it takes to create artificial gravity. So, why don't we build this torus? Unfortunately, this is because it's nearly impossible with our nowadays technology to build a such torus. Moreover, we lack of natural resources on Earth. The cost of such a project is also massive. The IS alone has a cumulative cost of $150 billion. Sending one single kilogram into space costs an average $18,500. The Empire State Building in New York weighs 365,000 tons, which would cost about $6,752,500,000,000 United States dollars to send into space, which is 3.3 times the PIB of Italy in 2019. Although we can't really build one spaceship once for all, we can get closer to that objective by progressively shipping materials into space. It could be a long-term project as it was with the ISS. It took nearly 30 years of construction to design and complete the International Space Station. Our spaceship might be the next one?